Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My course is going to help the students who are preparing for CSIR NEET, GATE, NT exam, PhD exam, SET exam, Jest, uh, TIFR, IIT-Jam, and other exams related to physics. So my courses are absolutely free of charges, so anyone can watch. And also guys, I thank you everyone for subscribing my channel, and I would request the people who have not subscribed my channel, please subscribe my channel. Okay, so today I'm going to teach you quantum mechanics, and this is going to be the first lecture of quantum mechanics. Okay, so I will start. Okay. So, okay. So, according to classical physics, right? Classical physics, if we have to describe any particle, so we can describe it by it's a momentum and energy. Okay, and also if we have to describe any wave, so we can describe a wave by its amplitude and its wave vector, which tells the direction of propagation of the wave, right? So, but I would like to inform you that the classical physics is not able to explain black body radiation, photoelectric effect, and Compton effect. So those phenomenon wasn't explained by classical physics, right? So here we are going to study black body radiation. Okay, black body radiation, right? But before that, uh, I will explain black body. So what is black body? Okay. I will write as well. Black body is material object. Okay, it is material object that absorbs and emit all the radiation. Okay, so so black body is the material object that absorbs all uh, all the radiation falling on it, and also when it is heated, it emits all the radiation. Okay, so that is the black body. For black body, we can consider a black body, right? A spherical cavity, right? There is a very small hole on the surface, and its walls are the inner walls of cavity perfectly reflect the electromagnetic radiation, right? So like this. And this is black body, we can consider. Okay. Okay, so this is the black body, right? So with the help of the classical mechanics, we are not able to explain black body radiation. For example, when we heat any solid object like metal, right? So it heats up and it releases electromagnetic radiation, right? And as we increase the temperature, after some time it becomes red, and as we keep on increasing the temperature, then it becomes yellow, and then again we keep on increasing the temperature, then it becomes white. And with the help of classical mechanics, we were not able to explain this. Okay, because in in classical physics, uh, we have what we consider is energy. Energy is continuous, right? And because of this, we were not able to explain black body radiation, right? So then we need to think energy in different way to explain black body radiation. But before that, I will make black body spectrum. Okay. Okay, just let me check. I'll make it again. So we have plotted different graph at different temperature. Okay. Okay, this is the spectral energy density U, which is function of nu and T versus frequency. We have plotted the graph, right? Frequency at different temperatures. So it is like this is at 2000 Kelvin and this is at 3000 Kelvin temperature, and this is as 4000 Kelvin. Okay, so this graph, this is the spectrum of black body radiation, right? And this graph wasn't able to explain by uh, classical physics, right? So I will also explain, and so physicists have done many experiments, and there is, I'll also explain this Stephen Boltzmann law. Stephen Boltzmann law. Stephen experimentally found that the total intensity total intensity that we can say total intensity means that is total power per unit surface area. Okay, that is total power per unit surface area. Total power per unit surface area, that is the definition of intensity. Okay, total intensity radiated. I'm writing it because it will help you. You can make notes as well, right? Radiated by a glowing object glowing object glowing object at temperature T at temperature T is given by I equal to A sigma T to the power 4. Okay, wait, just this one. Or power per unit surface area equal to A sigma T to the power 4, where sigma is Stephen constant. Okay, and the value of sigma is 5.67 into 10 to the power minus 8 watt per meter square per Kelvin to the power 4, right? So this is the value of Stephen constant, and we know that energy, the power is energy per unit per energy per second, right? So implies E proportional to T to the power 4. These formulas are very important formulas. Okay, okay, you can note down, and this is a very important formula. With this formula, there are many numericals you can solve. Okay, we'll solve the numerical based on this formula. Okay, and and there is a question which is asked in CSIR net using this formula. Okay, so this is the Stephen law, which is found experimentally during explanation of black body radiation. Okay, so now next page. Rayleigh-Jeans and Wiens also try to explain this the curve of the black body radiation. Okay, this is mu and this is u, energy density, which is function of mu and temperature. Okay, so I'm not going in derivation part because that is not required in net exam, gate exam, just right. So you need to solve the numerical questions. Okay, so I'm directly writing. So there's a Rayleigh's law, right? So we can write okay, Rayleigh's law. Or we can say Rayleigh's energy density distribution. Okay, so this is U, which is function of nu and T, is a nu cube. Nu is frequency. Okay, nu cube e to the power minus beta nu upon T, right? This is the Rayleigh's law, and Rayleigh's were able to explain only this part of the curve. Means at low frequency, Rayleigh's law is valid. So at low frequency, they are able to explain the curve. So they are able to explain this part of the curve. Okay, this part of the curve. Only this part of the curve they were that Rayleigh's law was able to explain. And then there is a Wien's energy density distribution, that is Wien's law. Wien's law. WI Wien's law. So here for explaining this and Wien's law is able to explain only right part of the curve. Means the Wien's law is valid for uh, higher frequency. Okay, not for lower frequency, but the complete curve is not explained by classical physics. Okay, so Wien's law is will write, and then for explaining Wien's law, Wien's considered the classical oscillator, and then he given the formula, he derived the formula, that is the energy density uh, U, which is function of nu T, is it is 8 pi nu square C cube, 8 pi nu square C cube into kT. This is the energy. Okay, average energy kT. This is the Wien's law. I'm writing all the formulas. Please note down those formulas. So these will help you to solve your questions in CSIR, NET, GATE, NT exam, and other exams. Okay. Okay. So Wien's Rayleigh's law is valid only at lower frequency, and Wien's law is valid only at higher frequency, right? But the complete black body the spectrum was not explained. Okay, right. So now Planck. So now we are going to Planck law, right? Planck's law. Planck's law. So Planck tries to explain the black body spectrum, the black body radiation, right? For that, uh, he considered this is the beginning of quantum mechanics, guys. Okay, so here Planck considered energy is not continuous, energy is discrete. Okay, it is called Planck hypothesis as well. So energy is discrete and it is in the form of packets called quanta, and energy is integral multiple of h nu, that is energy is quantized, and he has given energy equal to n h nu, where n equal to 0, 1, 2 integer multiple, okay, 3 so on, and h is Planck constant. Okay, from here the quantum mechanics started, guys. Okay, and the value of h is 6.626 into 10 to the power minus 34 joule second. Okay, so that's what he has considered, and then he considered harmonic oscillator. Okay, a quantum oscillator. Okay, and then he has derived average energy of the black body radiation, and that is average energy equal to h nu upon e to the power h nu upon kt minus 1. Okay, this is the average energy Planck derived using quantum oscillator. Okay, and the average energy of quantum oscillator is h nu upon e to the power h nu upon kt minus 1, where nu is the frequency, k is Boltzmann constant, k is Boltzmann constant. Okay, T is temperature and h is Planck constant. Okay, so this is the average energy of the quantum oscillator the Planck has derived. So we are not going into the derivation part because that is not required for the exam we are preparing for. Okay, and then he has derived the average energy density u, that is the function of nu and t, and that is equal to 8 pi nu square upon c cube h nu upon e to the power h nu upon kt minus 1. Okay, so this is the question, guys. Note down this. Okay, very important expression for energy density, and this is also very important. Average energy of quantum oscillator. Okay, average energy. So this is the energy density, and we can also express it in terms of lambda t, right? So since we know C equal to mu equal to C by lambda, right? And putting this value here, we can get energy density U, which is function of lambda t, is going to be 8 pi hc upon c cube, sorry, lambda to the power 5, lambda to the power 5 into 1 upon e to the power sc upon lambda kt. Lambda kt, lambda is the wavelength of the radiation, minus 1. Minus 1. Okay, so this is the energy density of radiation in terms of lambda t. Okay, so these you can note down these two formulas and this one as well, and also the Rayleigh-Jeans and Jeans law and Stephen's law. So all formulas are very important. Using those formulas you can solve many questions. Okay, okay, so now so since u, which is function of nu and t, equal to 8 pi nu square upon c cube h nu upon e to the power h nu upon kt minus lambda, right? This is the one, 8 pi nu square. So by this we can easily deduce Rayleigh-Jeans law and Wien's law, right? So like we are going to deduce Rayleigh-Jeans law from this. Okay, at lower frequency, at low frequency, at low frequency, at low frequency, at low frequency, h nu is less equal to kt, right? So it is like this. So in that case h nu is very less, right? It is less equal to kt. So in that case we can write u, which is function of t, equal to 8 pi nu square nu square 8 pi nu square upon c cube into h nu. So we can expand it because h nu is very small, so we can expand it till two terms only. So it is going to be 1 plus h nu upon kt minus 1, 1 1 get cancelled, h nu get cancelled, so it is going to be 8 pi nu square upon c cube into kt, which is Rayleigh-Jeans law, right? So intelligence. Similarly, we can derive or we can deduce the Wien's displacement law using Planck law. Okay, so this is the one. There is one more thing which I'm also going to explain. Okay. Also, guys, we can derive a total energy density. So since we know the energy density, that is U, which is function of mu and T, that is that's we know, right? 8 pi mu square upon C cube. H nu upon e to the power h nu upon kt minus 1, right? So now we can find out total energy density. Okay, so total energy density is going to be U is going to be we can find this in terms of Stephen Boltzmann's total power per unit surface area. It is going to be integration 0 to infinity 8 pi mu square upon C cube h nu upon h nu upon kt minus 1. Okay, let h nu upon kt, we can say x. So it is going to be total energy density 0 to infinity 8 pi mu square upon C cube x x. Okay, so here we are using this, right? Okay, so it is going to be 8 pi h C cube into x cube upon e to the power x minus 1 dx. Okay, dx it is going to be, it is okay. So we'll solve it, and by solving it, and we know, remember this, the integration of x cube upon e to the power x minus 1 is going to be 0 to infinity. This is the integration. You should know this value is 8 pi to the power 5 k to the power 4 upon 15 h cube c cube. Okay, you need to remember, right? So total energy density is going to be, after solving this, it is going to be 4 upon c sigma e to the power 4. So we have expressed total energy density in terms of Stephen Boltzmann's uh, total power per unit area. Okay, so where the value of sigma is 2 pi square, so 2 pi to the power 5 k4 upon 15 h cube c square. Okay, okay, right? So this is the one total energy density we have expressed in terms of Stevens Boltzmann total power per unit area. Okay, so this is also you should note down. Okay, and also here, guys, I need to tell one more thing, that is, I've explained Stephen Boltzmann law, right? for Stephen Boltzmann law for black body radiation. Okay, here value of A is constant. Here A is constant and value of A is less than or equal to 1. In case of black body radiation, value of A is 1. Okay, so here we can write E equal to sigma T to the power 4. For in case of black body, so total intensity is going to be I. Okay, so there is one more thing, that is Wien's displacement law. Okay, guys, I would just like to correct it. I said what I have explained is Wien's law. Okay, Wien's law and Wien's distribution law. So this is Wien's law. This is Wien's law. This is Wien's law, or we can say Wien's distribution law, Wien's energy density distribution law. Okay, so now we are going to study Wien's displacement law. Okay, Wien's displacement law. So this is a graph. This is nu and this is u, which is function of radiation using Planck hypothesis. Okay, so here this is the nu max. So we can say the highest, the peak energy density corresponding to nu. The frequency at peak energy is called nu max. Okay, so here the Wien's displacement says the frequency of peak energy density, that is nu max is proportional to temperature of the black body. Okay, temperature of the glowing object of black body, right? So nu is proportional to nu max is proportional to T, or since we know nu equal to C by lambda. Okay, so implies lambda max is proportional to 1 upon T, or lambda max is equal to B upon T. Okay, so lambda max proportional to, just write again, lambda max equal to P upon T. Okay, B is the constant, equal to constant. This is Wien's law, Wien's displacement law. This is as well. Okay, and the value of B is 2898.9 into 10 to the power minus 6 meter Kelvin. Okay, so this is the value of B. Okay, so okay guys, so I'm going to stop here, and thank you so much for watching my video. Now in next lecture I'm going to teach you mathematical physics, and this is going to be lecture number 1 of mathematical physics. Okay, so guys, thank you so much. Bye now.